Okay, so let us now prove proposition 6 to 5. So before we write the solution, let's recall the statement. In this proposition, we have any three extended real numbers, and we have to prove that the order relation we have defined on this set is, first of all, reflexive, that is, x is less than or equal to x. Then in part B, we have to prove trichotomy, that is, exactly one of these three statements is true. X less than y, x equal to y, and x greater than y. Then in part C, we have to prove that this relation is transitive, that is, if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. And in part D, we prove that negation reverses order. Negation reverses order, that is, if x is less than or equal to y, then it implies that minus y is less than or equal to minus x. We have to prove all these things, so we will do that one by one in the solution. So let us now see the solution. And there is a hint also. It says that we may need this proposition, which is just these properties but in the system of real numbers, okay, which we have already proved before. So we will use that. Let us now write the solution. Reflexivity is so easy that it's almost obvious. In place of this A, part A, we are going to write this. It follows from definition 6 to 3, which is the definition of the order relation on the system of extended real numbers, and reflexivity of the ordinary order relation on the set of real numbers. Then in part B, we have to prove trichotomy. Okay. We don't in fact have to assume x and y separately because it's already given there in the statement. So we start like this. We have two extended real numbers the case where both of them are actually real numbers is settled by that proposition. Proposition 547, which says that either x is less than y, or x is equal to y, or x is greater than y, and no two of these three statements can be simultaneously true. Note one more thing. Because of the way we have defined our order relation on R star, if we restrict our attention to this subset R of R star, then the resulting restricted order relation is actually the one we are familiar with on R. So that's why this proposition helps us settle this case. If x and y are both real, then we have our thing. Okay. So next, assume that both x and y are not real. If both x and y are infinite, that is, if none of them is a real number, then either x is minus infinity, and oh, I forgot to write that other thing, both x and y are not real. Okay. After this, we make another assumption. If x is equal to y, if x happens to be equal to y, in this case, under this assumption that both x and y are not simultaneously real, then if x and y are equal, then by definition we have this and this. Why do we have this, that none of these relations x less than y and y less than x is true? That is because x less than y is just a shorthand way of saying or writing these two things. So since x is equal to y, this statement is not true, which is just this. Similarly, y is not less than x. So if x is equal to y, then only that is true. The other two are not true. Thus, we now additionally assume that x is not equal to y. Okay. So now our case is this: x and y are simultaneously not real, and at the same time they are distinct. Now if both x and y are infinite, then either x is minus infinity and y is plus infinity or y is minus infinity and x is plus infinity. That is because they are distinct. So if one of them is plus infinity, the other is minus infinity and vice versa. In the former case, we have x less than y, and at the same time it's also important to mention that the other is not possible. Y not less than x, and in the latter case we have the opposite, that is y is less than x and x is not less than y. Okay, so this is when both x and y are infinite. Next, assume that exactly one of x comma y is infinite. So that means one of them is infinite and the other is real. We assume without loss of generality that x is infinite. That means x does not belong to the set of real numbers. Then y has to be finite. Now, depending on what x is, there are two cases. If x is minus infinity, then x is strictly less than y. And y is not less than x. On the other hand, if x is plus infinity, then y is strictly less than x and x is not less than y. So we have covered all the possibilities, and in each case we have shown that exactly one of these three conditions is true. So trichotomy has been proved. Okay, now we turn to transitivity. Part C. In this case, we have these two things. Here also, if our quantities are actually real numbers, then what should I write? Then the result follows from proposition. What is the number? 547. Yes. Okay. Also, the cases where at least one of the inequalities, this and this, is an equality. I need ink, give me a moment. Is an equality, and there are three such cases. Are easy to handle. Why do we say so? Let us see what the three cases are. The three cases are, of course, this. One of them is this: x is equal to y and y is strictly less than z. The other case is x is strictly less than y and y is equal to z. And the third case is that x is equal to both the inequalities are actually equations, and in each of these three cases you can see that it's trivial to conclude that x is less than or equal to z. For example, if you look at the first case, since x is equal to y, you just replace y with x, you get x strictly less than z, which just means x is also less than or equal to z. Similarly, for this one and this one, in this case you have equality. Okay, so two things we can now say. One is that we can now assume that all the three of these things, these numbers, extended real numbers, are not real, and at the same time both of these inequalities are strict. So we assume that not all of these are real and x is less than y and y is less than z. Now, this assumption has immediate consequence. First of all, note that due to the strict nature of both these inequalities, y cannot be infinite. Why? Because y is strictly greater than an extended real number, y cannot be minus infinity. Also, since y is strictly less than some extended real number, y cannot be plus infinity. So the first consequence is that y must be real, and for similar reasons x cannot be plus infinity and z cannot be minus infinity. Okay, so that means z can either be a real number or it can be plus infinity. Accordingly, there are now two cases. If z is equal to plus infinity, then x is of course less than or equal to z. In fact, x is strictly less than z. That is because x cannot be plus infinity. However, it's possible to have x equal to minus infinity. Whatever the case is, we don't care. We will always have this in this case. On the other hand, if z is a real number, then x is not a real number. Why? We assume that not all of these three are real numbers. Y is already compelled to be a real number. So now if z is also a real number, then x must be non-real. And hence x must be minus infinity, because x cannot be plus infinity. So the only way it can be infinite is when it is minus infinity. Which implies that again x is strictly less than z, because z is real, so minus infinity cannot be equal to z. So in this case also x is less than z. So we see that in all the cases we have x less than or equal to z. So transitivity has been proved. And now finally in part D we have to prove that negation reverses order. We have x less than or equal to y. Okay. The case x equal to y follows from, or instead of writing it like this, we can write the case x equal to y is settled by definition 6 to 2. Which is the definition of negation of an extended real number. So that is one thing. We thus assume that x is strictly less than y. Under this assumption, the case where x and y are both real, follows. When we write the case follows means the result in this case is true, and that fact follows from the real number version of this exercise 4 to 6. Okay, now I should make it clear why we have why we have written it like this. Why are we separately looking at this trivial case x equal to y? It's because let me first say what exercise 4 to 6 is. In exercise 4 to 6 we have two rational numbers x and y satisfying this inequality, and then we proved that minus y is less than minus x. Now exactly how we solve this exercise, one can do the same thing when x and y are real numbers, because properties of the order relation that is there on the system of rational numbers are similar to the properties of the order relation that we have on the system of real numbers. So one can similarly solve prove this implication if x and y are real. So that's why we are saying from the real number version of this exercise. And because in this exercise we have strict inequality, so we have handled the equality case separately. If one wants, one can just simply write all the things together instead of breaking them up into cases like this. Okay. So now x is strictly less than y, and x and y are not simultaneously real. So we now assume are not simultaneously real. So now three cases will occur. If x is minus infinity and y is a real number, because x and y are simultaneously are not simultaneously real, so either exactly one of them is non-real or both of them are non-real. So if x is minus infinity and y is real, note that since x is strictly less than y, x cannot be plus infinity. X, when it is infinite, it can only be minus infinity. Like that, when y is infinite, it can only be plus infinity, it cannot be minus infinity. So if this and y belonging to R, then minus y is also a real number, so minus y is less than plus infinity, but you can write plus infinity as minus minus infinity. by the definition of negation. And that is minus x. So we have proved that minus y is less than minus x. If on the other hand x is real and y is plus infinity, then minus y is, by the definition of negation, minus infinity, which is less than minus x, again because minus x is also real. And finally, if x is minus infinity and y is plus infinity, then minus y is minus infinity, which by the definition of order is strictly less than plus infinity, but plus infinity is minus of minus infinity, that is minus x. So in all the cases we have proved that negation reverses order. So that completes the solution and hence the proof of proposition 6 to 5. Okay, now in this section there is only one more exercise, so we are now going to look at that. The second one, prove theorems 6 to 11. The power has gone. Hint: you may need to break into cases depending on whether minus infinity or plus infinity, or plus infinity first and then minus, it does not matter, same meaning, will belongs to E. You can of course use definition 5.5.10. Provided E consists only of real numbers. Okay. This definition 5.5.10 is the definition of supremum of a subset of the set of real numbers. Okay, this we saw back then, in the place where we defined supremum of a subset of real numbers. So let us now first recall the statement of this theorem and then we will write the solution. I was supposed to film this last night itself, but due to some problem that was not possible. So I am having to do it now. So you may hear some faint background noises because we now have traffic outside. Anyway, tonight we will see a number theory video where we will see the third section of the first chapter. It will be a little history. It's titled Early Number Theory. So we will see what the author has to say. Okay. So let us now first recall the statement. In this theorem, we are given a subset E of the set of extended real numbers. In part A, we prove this. If x is in E, then x is less than or equal to the supremum of E, and also x is greater than or equal to the infimum of E. In part B, we have this. If capital M is an upper bound of E, then supremum of E is less than or equal to capital M, and in part C we have the lower bound version. If small m is a lower bound of E, then small m is less than or equal to the infimum of E. Actually, in the text again capital M is given, but it feels nice to use small m to denote the lower bound. Okay, so let's now see the solution. If we are not careful, then we may end up with many cases. I mean, of course, many cases will arise depending on you see the hint. You may need to break into cases depending on whether minus infinity and or plus infinity belongs to E. So it may happen that plus infinity is in E. At the same time, minus infinity is also in E, and the other case where it is not in E, and many such other cases. The job is to write the solution in a compressed manner without, of course, removing any essential detail. So let's see how the solution goes. That is, you have to make the solution. You don't have to, but it looks nice if we write a compact solution which has everything that we need. We first prove this. there is that other inequality also, we will prove it afterwards. Now the given statement is of course an implication. If x belongs to E, then this is true, and this implication is vacuously true if E is empty, so that case is settled immediately. If E is empty, then the above implication is vacuously true, because in this case the hypothesis of this implication, an implication has two parts, right? The first simple statement is the hypothesis, and the second simple statement is the conclusion. When the hypothesis is false, then the implication is vacuously true, and that's what is happening in this case. If E is empty, then the hypothesis is false. So we assume E to be non-empty. There is another case, or rather two cases, in which the implication is again true, but now not vacuously but trivially, very easily. Also, the above implication is trivially true if x is minus infinity or supremum of E is plus infinity, or both, which is included in this statement itself, because this or is inclusive or. If x is minus infinity, then this inequality is automatically true. Similarly, if supremum of E is plus infinity, then also this inequality is automatically true. Thus, we assume that x is not equal to minus infinity, and at the same time supremum of E is not equal to plus infinity. Now, what are the implications of these assumptions? All of these, that is E not being empty, and also these things. I should have assumed one element x, although we have x here, but this x is not something that we have chosen in E. It's a part of a conditional statement. If x belongs to E, then this happens. How do I write it in this confined space now? I have to. Okay, we will write it again. It's better to write things neatly instead of cluttering everything. After this, we assume this. Let x be in E. That is, x is any element in E. The above implication is trivially true if x is minus infinity or supremum of E is plus infinity. Thus we assume x is not minus infinity and supremum of E is not plus infinity. Oh, sorry, what am I writing? Is not plus infinity. Okay. Now, what do we have from all of this? Then, okay, now watch this. X belongs to E and at the same time x is not equal to minus infinity. So x then belongs to this set. From E we have removed minus infinity and hence this set difference is first of all non-empty. The empty set is a proper subset, or if this looks rather complicated, you can just simply write this. That's what matters. This is non-empty and this is a subset of R. Let us first understand this conclusion. Because x belongs to this set and x is something that has been chosen in E, so this set is non-empty. There is something in this set which is x. Okay. Then what about this being a subset of R? This set, because of the way we have defined it, already does not have minus infinity. We have removed minus infinity. If see, either E has minus infinity or E does not have minus infinity. Whatever be the case, this difference does not have minus infinity. Now, if plus infinity belongs to this, suppose plus infinity is there in this set, then since this set is a subset of E, plus infinity would then be in E also, but then by the definition of supremum of E will be equal to plus infinity, contradicting this assumption. So that's why it's somewhat indirect. I mean, of course you can see what I am saying here, but I am not going to make it a part of the solution. It follows from here that this cannot contain plus infinity and as a result it's a subset of R. So from this contradiction we see that plus infinity actually does not belong to this set, and it also at the same time does not have minus infinity. So it must have only real numbers in it. So that's why it's a subset of R. Okay. Now, this conclusion in turn has its own implication. This implies that supremum of this set is a real number. How? What is the reason for that? Note that now since this is a subset of R, so the old definition of supremum applies to it, which is this definition 5510. According to the old definition, because this set is non-empty, so supremum is not minus infinity. So that means the supremum is either a real number or plus infinity. If the supremum of this set is plus infinity, then since it's a subset of real numbers, it means one thing, that this set has no upper bound in R. Suppose that is the case. But if this has no upper bound in R, then its superset capital E also will not have any upper bound in R, and hence the supremum of capital E will also then be plus infinity, which again contradicts this. So that's why the supremum of this cannot be plus infinity. Or you can just simply, although this will be vague, understand it like this. If a subset has a supremum that is plus infinity, then the larger set also should have that supremum. So that's why supremum of this cannot be plus infinity either. So it has to be a real number. Okay, so this is one thing. Now we observe one more thing. Note that I think I have left substantial details from this solution. I mean, I'm just simply saying the things verbally. If you want, you can make them part of the solution. Okay. That is those parts where we say exactly why this cannot be minus infinity, also why it cannot be plus infinity, or for that matter, how we are getting this second part, and all of these things hinge on this assumption. Exactly how that you can write. Note that irrespective of minus infinity, belonging or not belonging to E, we have supremum of E equal to supremum of E minus infinity. This final conclusion that we have got, let it sit like that. This is something else. Okay. So note that okay, so what are we writing here? Irrespective of minus infinity belonging or not belonging to E, we will have this. But how? That is because plus infinity is already not in E due to this assumption. So that means E is a subset of this. Now there are two cases. Case 1 is this: minus infinity is in E. If minus infinity is in E, then by the definition of supremum, supremum of E is equal to this. We understand this. This is coming directly from the definition. This is what supremum of E means in this case. The other thing is this. In this case, the set E itself is equal to this, and so their suprema will be equal so that's why we are writing that irrespective of minus infinity belonging or not belonging to E, we have this. And I should perhaps mention this also, because we are getting this entire thing because of this. Now I notice something else. My claim that this solution is compact is not entirely true. It looks compact because I have left out many details. I see that now. Note that plus infinity does not belong to E, does not belong to E. Since supremum of E is not equal to plus infinity, and that is why we are getting this. Okay. We thus have X an element in this which is a subset of R, and so this is a non-empty subset of R whose supremum is also a real number. So it is the least upper bound of this set. Hence, this will be greater than or equal to every element of this set. In particular, it will be greater than or equal to X. And by what we have concluded here, this part, this is nothing but the supremum of E. So in this case also, X is less than or equal to the supremum of E. So we have completed the proof of this implication in all the cases. I would suggest you supply the missing steps. Missing steps means those things that I have just said and not written. Okay, next, we prove the other implication, or rather the other inequality. X is greater than or equal to infimum of E. Here also this implication is vacuously true when E is empty. We thus assume E is non-empty. Now let X be in E. Then by definition of the set minus E, minus X belongs to minus E. Thus by what we have proved above, minus X will be less than or equal to the supremum of minus E. So by proposition 6 to 5, part D of that proposition, that is the previous exercise, it's that part which is titled Negation reverses order, that part. X is equal to minus X. This we already know is true. It's true about negation of any extended real number. So minus X is less than or equal to this. So minus of that will be greater than or equal to minus of supremum of minus E, which by definition is the infimum of E. So that's how X is greater than or equal to the infimum of E. So this completes part A. Then in part B, it is given that capital M is an upper bound of E. M is an upper bound of E. If M is equal to plus infinity, then of course supremum of E will be less than or equal to M. If M is equal to minus infinity, then either E is the singleton set consisting of minus infinity, or E is empty. Now, how are we concluding this? If minus infinity is an upper bound for E, then we are saying that either E is empty or E is this. If E is empty, then fine, that is one thing. But if E is non-empty, say E is non-empty, then you choose any element x in E. Then because capital M is an upper bound, so x should be less than or equal to capital M, which is minus infinity. And this can happen in only one case, when x itself is minus infinity. So this arbitrary element of E has to be equal to minus infinity. That is the only element in E. So that's why these are the two possibilities. In either of these cases, we have supremum of E also equal to minus infinity. So in this case, supremum of E and M are equal, and hence in particular supremum of E is less than or equal to M. Okay. So that leaves us with only one case, namely when capital M is a real number. So we assume that capital M is a real number. Okay. Again, if E is empty, then supremum of E is minus infinity, which is now strictly less than capital M, because M is a real number, and again we are having the inequality that we want. However, if E is non-empty, then E is a non-empty set, and at the same time okay, E is non-empty since supremum, okay, now we are not saying anything about supremum yet. We are given that capital M is an upper bound for E, and at the same time E is non-empty, and the fact that capital M is R prevents plus infinity from being an element of E. Okay, then since plus infinity does not belong to E, this comes from we have supremum of E equal to supremum of E minus infinity, just like how we argued in part A. So this time also, because plus infinity does not belong to E, so supremum of E will be equal to this. Am I stretching it too long? If E is non-empty, then since we have supremum, no, this is not what I want to write. Then we have supremum of E not equal to plus infinity. And so, no, this cannot be nicely written in only one sentence. Now assume E is non-empty. Since M belongs to R, we have plus infinity not belonging to E, and hence supremum of E not equal to plus infinity. Let us see why supremum of E cannot be plus infinity. Because E is non-empty, so there are two possibilities. Either minus infinity belongs to E or minus infinity does not belong to E. If minus infinity does not belong to E, then of course supremum of E is just the ordinary supremum that you have in the system of real numbers. Why is that so? Because if minus infinity does not belong to E, then combining that with this other thing, E now becomes a subset of the set of real numbers, which is non-empty and it is bounded above by a real number. So by our least upper bound property, supremum of E is itself a real number, okay, and hence supremum of E is not plus infinity. But if minus infinity belongs to E, then again, since plus infinity does not belong to E, so supremum of E by definition is supremum of E minus infinity. Okay, now E minus infinity, this is a subset of R, So its supremum will then follow the old definition. If E minus minus infinity is empty, then its supremum is minus infinity. Otherwise, its supremum is again a real number, and hence supremum of E is again a real number. So supremum of E is either minus infinity or a real number. It will never be equal to plus infinity. The question is, should we write this? Is it not skipping too many steps and then writing this? I think so. What can we write then here? Okay, instead of skipping steps, let's just directly write the things. That will be, I think, much more clear. Plus infinity does not belong to E, as M belongs to R. We have okay. Under all these conditions, if E is a subset of R, then supremum of E belongs to R, and hence supremum of E is less than or equal to L. If E is a subset of R, then we are back to the system of real numbers, and supremum of E also belongs to R because E has an upper bound that is a real number and E is non-empty, and this becomes the least upper bound of E. So supremum of E is less than or equal to M from the properties of least upper bound of sets that we previously obtained, and particularly when they are real numbers. Okay. If minus infinity belongs to E, then supremum of E is equal to supremum of E minus minus infinity, again by the definition of supremum. Since E minus minus infinity is a subset of R, we have equal to minus infinity. This happens when E consists of just minus infinity. I mean, we come back to this case. Or since M belonging to R is also an upper bound of this subset. So if this subset is empty, then its supremum is minus infinity. And if it is non-empty, then it is also bounded above by capital M, because it's a subset of E and E is bounded above by capital M. So in that case, its supremum again by least upper bound property will be a real number. In the former case, we have supremum of E equal to supremum of E minus infinity equal to minus infinity. That is this case. This is less than M because M is a real number. And in the latter case, oh, I wanted to write all these things in one line. How is that possible? That's why I was not getting it. This is less than or equal to M. In the latter case means in this case, since capital M is also an upper bound for this set, so the supremum of this, which in this case is the least upper bound, literally the least among all the upper bounds, so it is less than or equal to capital M. And this we have already seen, we are under this case, that supremum of E is equal to supremum of this. So in all the possibilities, we have shown that supremum of E is less than or equal to any upper bound. So this completes part B. And now finally, in part C, we have this. In part C, we have to prove that small m is less than or equal to the infimum of E. If E is the empty set, then infimum of E, we have already seen this before, is plus infinity. The piston that is coming from minus infinity and moving rightward. If there is nothing to stop that piston in between, that is there is no E, then it will go without any obstruction and land at plus infinity. So that is the infimum, and hence small m is less than or equal to infimum of E. If you want, you can start this part by writing small m is a lower bound for E, or lower bound of E. Now assume that E is non-empty. Okay. Since small m is a lower bound of E, we have x greater than or equal to m for every x belonging to E. This implies minus x is less than or equal to minus m by proposition 6 to 5d. Negation reverses order, that thing. For all x belonging to E. Thus, minus m is an upper bound of minus E. So by part B, above, we have already proved that supremum of E is less than or equal to any upper bound. So in this case, supremum of minus E is less than or equal to minus m. Thus again, by proposition 6 to 5, its part D, m is equal to minus of minus m, that is will be less than or equal to minus supremum of minus E, which is nothing but the infimum of E. So this proves part C, and it completes this solution. So that just completes this set of exercises, which had only 2. In the next video, we are ending it here itself. We will start section 6.3, where we will see those things that I mentioned in the previous video also. Upper and lower limits of a sequence and limit points of sequences of real numbers. And tonight there will be a number theory video. So that will be all for this one. Let's see what we have in number theory, its early history tonight. So until then, this is me, Lucifer, from a mathematical room. Have a nice day.